Hello and welcome to Fun Facts Online. When you picture Western Europe, what's the first weather forecast that comes to mind? For a vast number of people, it's an image of perpetually gray skies, a constant, fine drizzle, and a landscape draped in a melancholic gloom. Of course, the sun-drenched shores of the Mediterranean and the crisp, snowy winters of the Alps are also part of Europe's diverse climatic tapestry. But the reputation for overcast weather, particularly in its western reaches like the United Kingdom, Ireland, France, and Scandinavia, is not just a stereotype, it's a meteorological reality. This persistent gloom isn't a matter of chance. It's the result of a complex and fascinating interplay of powerful forces, a dynamic dance between a massive ocean current, a fluctuating atmospheric pressure system, a relentless march of storms, and the very shape of the land itself. Today, we're going to pull back the clouds and dissect this atmospheric recipe, exploring the four key ingredients that create Western Europe's enduringly enigmatic and famously gray sky. Let's start with the fundamental classification of the region's climate. Western Europe is predominantly classified as having a maritime or oceanic climate. This is defined by a relatively narrow range between summer and winter temperatures. Summers are cool to warm, and winters are mild. But the most defining feature for our purposes is the frequent cloud cover and precipitation spread throughout the entire year. So what sets this all in motion? The first and arguably most significant player is a colossal force of nature you've likely heard of: the Gulf Stream. This isn't just any ocean current. It's a powerful and warm Atlantic current that acts as a planetary-scale heat conveyor. Originating in the tropical warmth of the Gulf of Mexico, it travels north along the eastern coast of the United States. It then veers northeast across the Atlantic, where its character changes and it becomes known as the North Atlantic Drift. This current is so influential that it's often nicknamed Europe's central heating. It brings an enormous amount of warmth to latitudes that would otherwise be significantly colder. To put this into perspective, consider cities like London and Berlin. They sit at roughly the same latitude as Calgary in Canada, or parts of Siberia in Russia, places known for brutally cold winters. Yet, thanks to the North Atlantic Drift, London and Berlin enjoy much milder winter temperatures, rarely experiencing the deep freeze of their latitudinal counterparts. The warming effect is truly profound. However, this thermal blessing comes with a very gloomy caveat. The Gulf Stream is a double-edged sword. As these vast quantities of warm water travel north into cooler regions of the Atlantic, a significant amount of moisture evaporates from the ocean surface into the air above it. Imagine a giant, warm bathtub in a cool room. Steam is constantly rising. The same principle applies here, but on an oceanic scale. This creates a huge mass of warm, moisture-laden air. Then, the prevailing winds in the mid-latitudes, known as the westerlies, come into play. These winds consistently blow from west to east, picking up this incredibly humid air and carrying it directly over the landmass of Western Europe. This creates a constant, unwavering supply of atmospheric humidity, which is the key ingredient for cloud formation and precipitation. As this moist air, which started its journey over a warm ocean, arrives over the cooler land of Europe, it begins to cool down. As air cools, its ability to hold water vapor decreases. The excess moisture has to go somewhere, so it condenses into tiny water droplets or ice crystals, forming the thick, extensive layers of stratus and nimbostratus clouds that are so characteristic of the region. So while we can thank the Gulf Stream and its extension, the North Atlantic Drift, for keeping Western Europe's winters from being unlivably cold, they are also the primary source of the very moisture that fuels its famously gray and damp weather. So the Gulf Stream provides the fuel, an endless supply of moisture. But what directs that moisture? What decides if a winter will be a stormy, wet washout or a cold, dry snap? That role belongs to our second major player, the North Atlantic Oscillation, or NAO. Think of the NAO as the grand conductor of Europe's atmospheric orchestra. It's a climatic phenomenon. a large-scale seesaw of atmospheric pressure at sea level. This seesaw operates between two semi-permanent pressure systems: the Icelandic low, a low-pressure center that usually hovers over Iceland and the surrounding ocean, and the Azores high, a high-pressure center typically located over the Azores Islands in the mid-Atlantic. The NAO alternates between two primary phases, known simply as the positive phase and the negative phase. The state of the NAO, especially during winter, has a dramatic and predictable impact on the weather across Western Europe. Let's start with the positive phase. When the NAO is positive, it means there is a greater than usual pressure difference between the Icelandic low and the Azores high. The low over Iceland is deeper, and the high over the Azores is stronger. This intensified pressure gradient is like turning up the power on the atmosphere. It results in a stronger jet stream, the high-altitude river of air that steers weather systems, and it pushes the main storm track into a more northerly path. The consequence is that powerful westerly winds push mild, moist Atlantic air relentlessly into northern and western Europe. This leads to winters that are significantly warmer and wetter than average. A positive NAO is strongly associated with an increase in storminess, bringing frequent and sometimes intense wind and rain to countries like the United Kingdom, Ireland, France, and Scandinavia. While it means milder temperatures and less snow, it also translates directly to more days of unsettled, cloudy, and rainy weather. It's the classic recipe for a gloomy European winter. Conversely, we have the negative NAO phase. This is characterized by a weaker pressure difference between the Icelandic low and the Azores high. The low-pressure system is weaker, and the high-pressure system is also less intense. This results in a weaker, more meandering jet stream that tends to buckle and follow a more east-to-west path, often dipping southwards over the Atlantic. This southern shift in the storm track effectively acts as a block, preventing the usual flow of mild Atlantic air from penetrating into northern Europe. As a result, this region experiences colder and drier conditions, with a noticeable decrease in storminess. The moisture and the storms don't just disappear, though. They are redirected. In a negative NAO phase, the storm track shifts south, bringing wetter and stormier weather to the Mediterranean region and southern Europe. So, while a negative NAO might mean fewer rainy days for someone in Scotland, it often comes with a trade-off: much colder temperatures and an increased potential for significant snowfall. The NAO's behavior is fascinatingly complex. It can remain locked in a particular phase for weeks or even months at a time, especially during the winter, which largely defines the overall character of the season. Its unpredictable, oscillating nature adds another layer of variability to Western Europe's already notoriously changeable weather. We have our moisture source from the Gulf Stream and our directional influence from the NAO. Now we need the delivery mechanism. This is where the North Atlantic storm track comes in. It's a veritable highway for low-pressure systems, the engines of foul weather. The constant procession of these systems, technically known as extratropical cyclones, across the North Atlantic is a fundamental reason for Western Europe's gloomy reputation. These cyclones are the primary drivers of widespread, persistent precipitation in the mid-latitudes. The North Atlantic storm track is one of the most active and energetic in the entire world. It represents the preferred path these cyclones take as they are steered by the jet stream, traveling from west to east across the ocean. The genesis of these storms is fascinating. They are often born over the warmer waters of the Western Atlantic, sometimes off the coast of North America, where there's a strong temperature contrast between cold polar air and warm subtropical air. This temperature difference provides the energy for the cyclone to form and intensify. As these developing storms move northeastward over the open ocean, they draw in the abundant moisture and thermal energy provided by the warm waters of the North Atlantic Drift, effectively fueling themselves and growing more powerful as they travel. Their journey, guided by the jet stream, often takes them on a collision course with Western Europe, with the UK, Ireland, Iceland, and the Nordic countries being particularly exposed, sitting right in the path of this atmospheric conveyor belt of storms. The arrival of one of these mature cyclones brings with it all the classic signs of unsettled weather that Europeans know so well. A rapid fall in barometric pressure, a thickening and lowering of cloud cover from high cirrus to dense, gray nimbostratus, and the inevitable onset of precipitation. The rain or snow from these systems is often cyclonic or frontal in nature. This means it is widespread, covering large areas, and can be remarkably long-lasting. It's not the short, intense downpour of a summer thunderstorm, but rather hours of persistent drizzle or steady soaking rain that can go on for an entire day. As we discussed, the frequency and intensity of these storms are heavily influenced by the North Atlantic Oscillation. During a strong positive NAO phase, the storm track is more robust, more northerly, and aimed like a cannon at northern Europe, leading to more frequent and powerful storms, sometimes called European windstorms. In a particularly interesting crossover, even the remnants of tropical cyclones, such as hurricanes that form in the tropics, can get caught up in the westerlies. They can travel all the way across the Atlantic, lose their tropical characteristics, and transition into powerful post-tropical storms. These can then merge with the existing storm track and impact Western Europe with unusually strong winds and heavy rainfall, adding another element of extreme weather to the mix. We now have our final key element in this meteorological puzzle, a process that happens right at Europe's doorstep: orographic lift. This is where the continent's own varied topography, especially its mountain ranges, plays a crucial role in enhancing precipitation and making its own weather. Orographic lift is a simple concept with dramatic consequences. When the moisture-laden westerly winds we've been talking about, flowing in from the Atlantic, encounter a significant physical barrier like a mountain range, the air has nowhere to go but up. It is forced to rise over the terrain. As this parcel of air ascends, it moves into lower pressure at higher altitudes, causing it to expand and cool. This process is known as adiabatic cooling, just like we saw with the air cooling over land. As this rising air cools, its capacity to hold moisture plummets. The water vapor is forced to condense into clouds, and if there's enough moisture and uplift, it precipitates as rain or snow. This effect is particularly pronounced on the windward slopes of mountain ranges. That is, the western-facing slopes that directly face the incoming moist winds. These areas become rain-making machines. The western coasts of Scotland, the mountains of Wales, the western fjords of Norway, and the western slopes of the Alps are all prime examples of this phenomenon. These regions receive significantly higher rainfall totals than areas just a few dozen kilometers to the east. The air that eventually descends on the leeward, or eastern side of the mountains is now much drier because it has released most of its moisture. As this dry air descends, it compresses and warms up, further reducing humidity. This creates a rain shadow, a region of significantly less precipitation and often clearer skies on the downwind side of the mountains. For example, the city of Bergen on the west coast of Norway is one of Europe's rainiest cities, while Oslo, on the eastern side of the country, is considerably drier. This orographic effect means that even within a relatively small geographical area, there can be dramatic differences in rainfall and cloud cover. It's the force that contributes to the lush, green, almost magical landscapes of Western Europe's coastal and mountainous regions. But it does so by literally wringing out the atmospheric moisture in the form of frequent rain and low-lying clouds, often enveloping the mountain peaks in a persistent, moody fog for days on end. So when we put it all together, the perception of Western Europe as a persistently gloomy region is not just a cultural trope, but a meteorological reality rooted in a powerful and beautiful convergence of factors. It's a four-part symphony. First, the warm waters of the Gulf Stream and North Atlantic Drift act as the fuel, the great engine, providing an almost infinite supply of atmospheric moisture. Second, the North Atlantic Oscillation acts as the grand conductor, using its pressure fluctuations to direct the flow of this moisture. with its positive phase in particular steering a barrage of wet and windy weather towards the north. Third, the North Atlantic storm track provides the vehicle, a relentless highway for low-pressure systems that carry this weather across the ocean and deliver it with widespread, long-lasting precipitation. And finally, the region's own topography, through the process of orographic lift, gives the atmosphere one final squeeze, ensuring that any remaining moisture is released as rain or snow over the western highlands. While the sun does, of course, shine in Western Europe, the ever-present influence of the vast Atlantic Ocean and the complex atmospheric dynamics it engenders mean that gray skies and a scattering of rain are never too far away. It is this very gloom, however, that has sculpted the region's verdant landscapes, filled its mighty rivers, and shaped the culture and resilience of its inhabitants. But before we go, here's a final thought-provoking fact. Despite this deeply ingrained reputation, recent data, published by the Copernicus Climate Change Service, has shown a surprising and significant trend over the last 4 decades. Across much of Europe, there has been a measurable decrease in average cloud cover and a corresponding increase in sunshine duration. This is a potential sign that the larger forces of global climate change are beginning to alter even this long-standing and powerful weather pattern, adding yet another layer of complexity to the future of Europe's famously enigmatic skies. Thanks for listening to Fun Facts Online.